Hello everybody, welcome back to this training on neural network and deep learning. This is the second video of the series in which we will discuss how we can combine individual perceptrons together to build up something that is called a neural network. So in terms of a quick recap, so what we looked at in the first video is we looked at what are the fundamental building blocks of neural networks, and we call them as perceptrons. And we also looked at how perceptrons receive information from of different type, which are potential influencers of the final decision, and then how these information are combined together in order to arrive at the final decision using a weighted linear combination of this individual informations and then comparing them with a threshold. So this is how the decision making works. So if there are p factors or p features from where the informations are being fed in, then they are combined in this way by a weighted linear combination and then compared with a threshold, and depending on the comparison result, whether or not this combination is bigger than the threshold b or less than the threshold b, the output decision is arrived at. And we also concluded that it's a very intuitive and effective way of combining different sources of information to arrive at a decision, and the decisioning model actually depends on the choice of weights w and the b. So given a set of x's, what kind of decision will be arrived at depends on both the weights and the threshold b. And then we intuitively said that if a single perceptron can do simple decisioning tasks, then it's very logical that if we can put together a collection of perceptrons in some shape or form, then it can be very effective for complex decision making. And in this video, what we will see is how exactly we can combine perceptrons together in a particular shape or in a particular form. So if I think of a setup where there are p x variables, and these x variables are as you would have seen previously, these are the different features or the different factors which are potential influencers of the final decision. So these are basically the information that you have at hand, and then think of it that based on these x variables there is some decision which is to be arrived at. So if you think of the example we looked at in the previous video, there were three factors, three features or three set of information we were considering, which were namely the how the weather is going to look like, and whether or not you will have good company in the form of who is accompanying you to the venue, and the third factor was whether or not there is parking available near the venue. And using these three information, we wanted to arrive at a decision that whether or not you want to go for a particular event in the town, which in fact was a food festival. So that was the setup there. Here we are looking at a similar setup, a more generalized form. There are p features on which there are informations available, and assume that here we are up to a very complex decisioning task for which maybe one neuron is not sufficient. So in the initial example, when there was just one neuron, all the features were actually sending their information to the single neuron. So if instead of having one neuron, we have now three neurons, it's very intuitive that all the features will be sending information to all the three neurons instead of one single neuron. So that is quite straightforward and quite intuitive. So if you look at this diagram here, there are three sets of lines, and each set actually has four lines, right? So one of the set is the set in blue, the other one is the set in red, and the last one is the set in green. And each color set actually has four lines. So the four lines in the blue set are basically the information from x1, x2, x3, and xp, which is going into the neuron N2. Actually, there will be not four but p lines out here, because there are p features that I am considering, but I have just plotted four just to keep things clear. Okay. So each feature is actually sending their information to each of the available neurons out here, and each neuron is doing a decisioning task that a perceptron does, right? So and the decisioning task is of the nature, it computes a weighted combination of the features, summation wixi, and then compares it with a threshold, and then arrives at a decision. Now, if you would have already noticed, I have introduced the term neuron here. So what I was calling as perceptrons, I'm already calling them as neurons. So this might trigger a natural question that are these synonyms, all but the same? Hold on to this thought for the time being. We will get this clarified by the end of this video. So so essentially, there are okay. So since we called them perceptrons at the beginning, let's go ahead and call them perceptrons here as well. So there are three perceptrons, and each perceptron is doing a decisioning of this form. And point to be noted here is that the weights, which is the W's and the B's, are different for different perceptrons. So the choice of weights need not be the same for all the three perceptrons, right? So the setup is the p there are p many features or p many factors out here, and all of them are sending signals to sending information to each of the three perceptrons, and then each perceptron is doing a decisioning of this nature, and the weights involved in the decisioning can potentially be different for all the three neurons. Now, if there are three perceptrons or three neurons which are present out here, each one is doing a decisioning of this nature, then our purpose is still not solved, right? Because at the end of all these, we want one single decision. We don't want three decisions, right? So what we do is we very conveniently we put in another perceptron here, right? And what this perceptron will do is this will fetch the decisions from the previous three perceptrons and combine them to arrive at a unified decision, right? So if you think of it in this way, that each of these perceptrons, they were receiving information from the input features and doing some decision making, and now each of these perceptrons, they are passing on the N1, N2, N3, these three perceptrons, they are passing on their individual decisions to N4, and N4 is then again combining them. And how it is combining them? It's a perceptron, so it is combining them in a way in which perceptrons make decisions. So it's again doing a linear combination of this nature, but in this case the linear combination is not of the x's. So though I have used x as a common notation here, but what N4 is doing, it is not doing a linear combination just of the initial x's, but it is doing a linear combination of what is coming out from N1, N2, and N3. And obviously there are some weights involved, which is the W's and the B's, and these W's and B's are another new set of weights, right? And N4 actually gives us the final decision. So that is how this entire thing is set up. And if you would have guessed by now, it's possible to extend this even further. So initially we were having just three neurons, N1, N2, N3, or three perceptrons, and then each one of them was doing some decisioning, and then their decisions was finally getting combined by another perceptron. Now we can introduce another layer out here, right? So let's, instead of having n1, n2, n3, we could have had n4, n5, n6. And then what n4, n5, n6 would do is they would again, each one of them, they would again get the decisions which are being done by n1, n2, n3. So if you see, n1 is flowing into n4, n2 is flowing into n4, n3 is also flowing into n4, and similarly they are flowing into n5 and n6 as well. And then n4, n5, n6, they will give me some decisions in the same way as perceptrons make decisions, and finally their decisions will have to be combined by this final perceptron in 7 to give me the final decision. So it's possible to, you know, add more layers like this. Just that, you know, more the number of layers that you add, there are more weights that you are introducing to the scenario, right? Because these each of these perceptrons in their decisioning process, they will involve different weights, different W's and different B's. So all of them have to be estimated, right, at the end. So more complex you make this stuff, more weights you are introducing into the scenario. Now, by now, uh, the figure, the structure that you're looking at here is I'm sure it's pretty familiar to how what a neural network looks like, that you would have seen as an image, right? So this kind of a structure is generally called a feed-forward neural network, or it's also at times called a multi-layer perceptron network. Now, why it is called a multi-layer perceptron network? It's very intuitive, because it's built up based on multiple layers of perceptrons, right? And potentially you can have any number of layers that you want to. And it's also called feed forward neural networks, because if you see, the flow of information is in one direction. So it starts from the input features x1, x2, xp right at the left hand side, and then from there these informations are fed into the first layer perceptrons. These perceptrons do some computation, some decisioning, and then they pass on their uh, decisions or informations to n4, n5, n6, and then they do some decisioning, and then finally their decisions are combined by the terminal perceptron n7 to give the final decision. So flow of information is from left to right in the forward direction of the network. That is why these neural networks are also called feed forward neural networks. Now, you might be thinking that it's fairly obvious that the information will flow from left to right in the forward direction of the network. How can it flow the other way around? Because x1, x2, xp are the input features, and n7 is where the final decision is being arrived at. So information can only flow from left to right. So what's the big deal in calling it a feed-forward neural network? But later on, we will see that there are networks that we can construct where information can flow in the reverse direction as well, and there are specific reasons, specific purposes for which those kind of networks are used. So for now, uh, it's sufficient to know, that these kind of structures are called feed-forward neural networks or multi-layer perceptron networks, and I also explained why these names, how these names are derived, and this is one of the most simple and popular form of neural networks that you will get. And as you would have seen that the starting from the fundamental building blocks, which is the perceptrons, we ended up building up this kind of a network, the feed-forward neural network, and potentially it's possible to add more layers out here. So the intuition that we started off with, that perceptrons, since they are very effective in combining different observed factors to arrive at a decision, our intuition was that if a single perceptron can do simple decisioning, it's possible to combine a collection of those perceptrons for doing more complex decisioning. So we have kind of justified that intuition, and we have also seen that more complex the decisioning is, we can potentially build more complex looking networks, we can pretty much stack layers of perceptrons like Lego blocks, right? As kids, we used to build structures out of Lego blocks by stacking them together. So here also, for complex decision making, we can stack different layers of perceptrons and make the network more complex, of course at the cost of introducing more weights into the entire system. Okay, so that's pretty much about how perceptrons can be combined to build neural networks, and in the simplest form of neural networks, which is the feed-forward neural network. Now, we conclude this discussion, this video, there's one thing that I'll quickly touch upon, and it will also clarify the fact that whether these individual units, the fundamental building blocks, whether to call them perceptrons or to call them neurons. Okay, so to be able to do that, we will first look at a mathematical representation of the perceptron decisioning. So how does a perceptron do decisioning? Can we represent it mathematically? We actually can. So if this is a perceptron, then the decisioning pretty much happens like this. So the output decision is 1 if this linear combination of the input features is more than b, and the output decision is 0 otherwise. So this is how the decisioning occurs. Now this decisioning model can actually be written as a combination of two mathematical functions g and a. We are calling them g and a out here, where the function g is actually doing the linear combination. So g, when applied on the input features, it is actually doing the linear combination wixi plus b. So we are just bringing b to the left hand side out here, and then we can easily say, so we can so okay, so instead of plus, you might be wondering that it can be minus as well, but then b is a constant quantity, right? I mean, you can easily think that negative sign to be absorbed in the constant quantity, and still write this as plus, right? So I could have written instead of b, I could have written here some k, where k equal to minus b. But that's a cosmetic thing. So we can write g as a function of x1, x2, xp in this form, summation wixi plus b, and then we can think of another function a. What it does is a of z will be 1 if z is positive, and it will be 0 otherwise. So we can define a function a like this, which outputs 1 if its argument is positive and outputs 0 otherwise. Combining g and a, you will see that the output decision from the perceptron is actually a composite function. So it's a of g of x1, x2, xp. So g of x1, x2, xp will actually give us this linear combination, and then a of that quantity will give us the decision as 1 or 0, depending on whether g of x1, x2, xp is positive or negative, right? And it's pretty straightforward. And this function a is actually called the activation function, right? And activation functions actually have a huge role to play as far as neural networks are concerned. And in the next video, or in the one after the next video, we will have a detailed discussion on activation functions. Because they're a very key concept of the neural networks, but here we are just introducing the concept of activation function. In this case, the activation function has this kind of a form, right? So it gives a value 1 if the argument of the function is positive, and gives the value 0 otherwise. Now there can be different other forms of activation functions as well. So this is just one particular choice of activation function. So with that discussion done, now I'll come back to the question, right, which I posed in in this video that whether I should be calling this a perceptron or I should be calling this a neuron. Are they synonyms? So the answer to that is I should be calling them as these units as neurons in a more generic sense. But if I'm choosing this kind of an activation function, this form of an activation function, then these neurons are called perceptron neurons. So any neuron which has an activation function of this nature is actually called a perceptron neuron. Now if I change the form of the activation function to something else, then obviously this neuron will not be called a perceptron neuron. So it can be a different neuron then, right? So answer to the question is yes, we can call the more generic way would be to call these building blocks, individual building blocks, as neurons. But with this particular choice of activation function, they can be called as perceptrons as well. And the reason I kept calling them perceptrons all throughout was because the example that we started off with there, the activation function was of this nature, where the activation function is giving a 1 or a 0 value depending on the sign of its argument. So to summarize, the examples that we have looked at perceptron neurons, because we have looked at this kind of an activation function, but further down the line we will see different other choice of activation functions and different other kind of neurons. But the fundamental building blocks in a more generic sense for neural networks would be neurons, and perceptrons are a particular kind of neuron. Okay, so what did we, if I summarize, so what did we look at in this video? So we looked at how perceptrons can be combined to arrive at something that is called the neural network, and then we looked at the structure of the feed-forward neural networks and how we can make them more complex by adding layers of perceptrons. And then we also looked at how mathematically we can represent the decisioning which is done by a perceptron, and then we introduced the concept of the term activation function, and then we clarified the fact that whether or not this with this fundamental building blocks of neural networks to be called as neurons, or should they be called as perceptrons. So we did that clarification, and now the stage is set for us to actually go into the crux of the matter, or the core topics, which are activation functions, and then of course how the weights, the W's and the B's, are estimated so that the neural networks can deliver the decisions, can estimate the decisions that they are designed for. So that's all for this video. Thank you for watching. Stay tuned for the next one. Bye bye.